Hi everybody, I'm coming to you today from my socially distanced home shop due to the COVID-19 pandemic. The purpose of this video is to provide some information that will help you get better results when using screws to fasten parts together. If you're already an expert at choosing and using screws, there's probably very little reason for you to continue watching this video. But if you've never used screws, or if you've ever experienced any of the following problems when trying to use screws, stick around. I think you'll find this video very helpful. We've seen some of the things that can go wrong when using screws. Now let's take a look at the tools and techniques needed to avoid these problems and ensure a nice, neat installation every time. First, we'll gather all the tools and materials that we're going to need. We'll need the parts that we want to fasten, appropriately sized screws, the correct driver for the screws, a variable speed drill, preferably cordless, appropriately sized drill bits, a countersink, masking tape, a ruler or tape measure, a pencil, and clamps if you have them. Before I begin using everything that I have assembled, I want to show a series of slides that illustrate the process of preparing your wood to accept the screw. I find, when I'm trying to learn by watching, that it helps to know what the goal is first. That way I can focus my attention on how and why the presenter is doing things, rather than wondering what she is doing. We'll get to the why and the how in a minute, but right now we'll take a look at what preparation needs to happen to ensure flawless screw installation. This first slide shows a simplified section cut of two boards as represented by the brown rectangles. Here we see a hole drilled through the top board and into the bottom board. The total depth of this hole will be just a little deeper than the overall length of the screw that we'll use. The diameter of this first hole will match the diameter of the screw shank, not including the threads. Next, the second, larger hole is drilled, but only through the top board. The diameter of the second hole should match the diameter of the screw shank, including the threads. The final step in preparing your wood to accept the screw is to use a countersink bit to create a cone-shaped recess to house the screw head, allowing it to sit flush or slightly below the surface of the top board. Once the wood is properly prepared, the screw is twisted into place using the appropriate driver. Now that you've seen what needs to happen, I'll take you through a couple of examples and explain how I make the choices that I do and why I do each step of the process. I'll start with these two small white oak boards. I want to screw through the face of one of the boards and into the edge of the other so the boards will be joined at a right angle. I'm going to want the screws to be centered in the thickness of the bottom board, so I need to measure. In this case, the thickness is 3/4 of an inch, so to find the middle, I simply double the denominator, that's the bottom number, to divide the fraction in half, and now I know that I need to locate the screws 3/8 of an inch in from the edge of the top board. I'm going to keep the screws an inch from the ends of the boards, which is usually as close as I like to get from the ends, to minimize the risk of splitting the wood. If you properly prepare the wood and use good technique, you can get closer than that without splitting during installation. But the connection becomes inherently weak if you get too close to the ends of your boards, and it may split during use. These boards are about 2 inches wide and 3/4 of an inch thick, so that gives me a total of 2 3/4 inches of wood depth when the two boards are in position for fastening. For furniture scale projects, I rarely see the need to have more than 3/4 of an inch to an inch of thread engagement. The exception to that is if the screw is engaging in end grain, since the screw threads cut the wood fibers into short sections, which makes it easy to accidentally strip the screw hole during installation. For end grain, I like to have about 2 inches of thread engagement. In this case, the wood fibers are running more or less parallel to the threads, and the threads won't cut them into short segments. So I've chosen a 1 5/8 inch long screw that will have about 7/8 of an inch of thread engagement. Now that I have the screws picked out, I can find the appropriately sized drill bits to drill my pilot holes. I just start with one that looks close to the diameter of the screw shank minus the threads and take a look. I want to find a bit that is small enough to allow the entire screw thread to engage with the wood, and yet big enough that the shank doesn't force the wood to split. Slightly small is better than too big for this step. Next, I need to find a bit that is big enough to allow the screw to pass through the top board without engaging the threads. Again, I just compare the drill bits to the screw until I find a good match to the diameter of the threads. Whenever possible, I will clamp my parts into position before drilling pilot holes and installing screws. I'll start by lightly tightening the clamp so that I can accurately align the pieces. This is a good time to be fussy because if the pieces are out of alignment when the pilot holes are drilled, it will be impossible to align them without drilling new holes. Once the parts are aligned, I go ahead and tighten the clamps. One final check to make sure everything remains aligned, and now I'm ready to drill with the smaller diameter bit. It is important to keep the bit perpendicular to the wood surface and not angle it significantly left to right or front to back. Drilling at an angle will tend to pull the pieces out of alignment when the screw is tightened. It's also possible to angle the pilot hole to the extent that the screw can poke through the side of the bottom board. You'll see that I frequently pull the bit back out of the hole while it's still spinning forward. The reason I do this is to clear the wood chips from the grooves or flutes in the bit. With these small drill bits, there's not much room for the chips to work their way out of the hole, so they tend to pack tightly into the flutes, where they cause a lot of friction, and, because the flutes are blocked, it becomes much harder for the bit to advance into the wood. The bit will be hot, so I tend to use a screw to scrape the chips out of the flutes. I often see people reverse the drill when pulling the bit out of the hole, but that tends to leave the chips in the hole, and we really want to get them out of there to provide room for the screw. With the first hole drilled, it's time to drill the larger hole. Since I only want to drill through the top board, I need to be able to tell when I've gone deep enough. I'll use a small piece of masking tape to mark the bit at the depth of the thickness of the top board. The tape provides a visual clue only. It does not prevent the bit from drilling deeper, so it's up to me to lift the drill as soon as the tape starts to scrape the chips from the surface of the wood. The larger bit will drill more aggressively because it is enlarging an existing hole, so I need to be extra careful not to drill too deep. You may be wondering, why drill the larger hole? Wouldn't the small hole prevent splitting in both boards? It is true that the small hole will prevent splitting, but allowing the threads to engage with both boards often creates a gap between the boards that no amount of driving can close. Here's what happens. The threads are engaged in the top board, so the screw is advancing at a set rate with every revolution. When the screw gets to the second board, it may take a partial revolution or even more for the screw threads to bite into the wood. During the time that it takes for the threads to catch, the screw point is pushing the boards apart. Now there's a gap between the boards, and that gap is maintained by the screw threads. No matter how many times the screw revolves, the gap will remain the same because the screw threads are acting equally on each board. By eliminating the thread engagement with the top board, we ensure that it will be pulled tight to the bottom board as soon as the screw head is seated. So I have my two differently sized holes drilled. If I were using screws with heads designed to sit on the surface of the wood, I would now be ready to install the screws. In this case, I'm using bugle-shaped screws that are designed to sit flush to or slightly below the wood surface, so I need to use a countersink bit to make room for the screw heads. I simply center the countersink bit in the hole and drill until I have enough clearance for the screw head. If I see that the countersink hole is getting off center, I correct by leaning the drill slightly in the direction that the hole needs to move. The wood is now prepped and ready to receive the screws. Once I have mounted a number 2 Phillips driver bit into my drill chuck, I need to optimize my drill for driving screws. Most cordless drills have 2 speed ranges. I've been using the higher speed range to drill the holes, and now I'm going to shift to the lower speed range. This will give me more control and make it less likely to strip the screw head. Most cordless drills also have 2 modes, drill mode and drive mode. The difference between the two is that, when in drill mode, all the power that the drill can produce is available to the bit. The bit only stops turning if the motor stops. In drive mode, the power of the motor is directed through a mechanical device called a clutch, which allows us to set the amount of power or torque available to the bit. This is a huge help to avoid overdriving screws or breaking off screw heads. I'm going to set the drill clutch to a fairly low setting to start. I can always increase the torque if needed, but with a properly prepared pilot hole, I usually don't need a lot of torque. If the clutch is set too low and the screw doesn't seat all the way, I'll simply back it out a bit, set the clutch a bit higher, and re-drive. Ideally, the screw will fully seat an instant before I hear the clutch engage. I want to talk a little bit about the technique involved when using a drill to drive screws. The driver bit should engage the screw head as straight on as possible. Leaning or canting the drill will result in poor engagement, which allows the bit to jump out of the screw head or to slip. This will wear out the bit and strip the screw head. It is inherently difficult to keep a drill bit straight because the handle is not in line with the center of the bit. This is another reason that I use clamps to hold my work whenever possible. Using clamps frees up my other hand to apply pressure to the back of the drill directly in line with the bit. As I begin to drive, I apply light pressure on the screw, and as more of the thread engages with the wood, I increase the pressure. It is important to realize that the screw will be moving away from the driver bit as it advances into the material. The drill must be pushed toward the screw to keep the bit engaged with the screw head. Most stripped screw heads are caused by incorrect alignment between the driver bit and the screw head and/or inadequate pressure on the screw throughout the process. Whenever possible, I prefer to set up so I can drive screws from the top rather than from the side. I also find it easier to maintain good pressure on the screw when it is located around waist height or lower. This may mean that I need to move my project off the workbench and onto a stool or even the floor. So you can see that these screws went in easily. The heads are still in good shape, and they're sitting just below the surface plane of the top board. The joint is tight and strong, and has remained in alignment. I want to show one more example. I've mitered a simple molding to make a tiny model base. I need to screw some ledger boards to the inside to provide support for an inset top. I'll be attaching the ledger board to what will be the inside of the base, and I need to make sure that I choose a screw that is long enough to have good thread engagement, but not so long that it pokes through the front of my piece. If we look at this screw lineup, we can see that the first two screws on the left would poke through, while the first two screws on the right would not have good thread engagement. The one in the middle is a winner. I don't like to use screws that will get closer than 1/8 of an inch from the face of the second board, because there's too much risk of accidentally drilling all the way through with the pilot hole. Also, if the screw is almost as long as the combined thickness of your pieces, and you get a little carried away with the countersink bit, the point of the screw will poke through. Now that I have selected my screws, I'll select two bits in the same way that I did in the previous example. I'll mark both bits with masking tape this time, since the depth of the first hole is also critical. It's actually easier to tape the bit before mounting it in the drill chuck, so I'll go ahead and do that. You can see that I have the smaller bit marked at the overall length of the screw. The larger bit is marked at the thickness of the ledger board. I have to be very careful when drilling my pilot holes because I could easily drill through the face of my base. Remember, the tape is only a visual cue. It will not stop you from drilling deeper. From this point, the process is the same as before. Set the drill speed to high and the mode to drill for the pilot holes. Drill the small holes through the top board and into the bottom board to the depth of the screw. Use the larger bit to enlarge the holes in the top board. Use the countersink bit to make room for the screw heads. Set the drill speed to low and the mode to drive. Set the clutch to 4 or 5 to start. Use the correct driver bit to drive the screws. And enjoy the satisfaction of a job well done.